Today I'm going to talk to you guys about Newton's second law. If you recall, the first law says that for an object in motion, it will tend to stay in motion, or at rest will tend to stay at rest, unless acted upon by an unbalanced external force. So we talked about that during last unit. This particular law is kind of an important one. It's the one that set physics on the more mathematical path that it's taken since the late 1600s. So Newton had a lot of good insights in his lifetime, probably more than any one person should have. But this is a big one, and so let's talk about it here real quick. I just want to remind you of a couple things before we get started too far into it. The first is that mass has this property we call inertia, and so inertia is a resistance to a change in motion. So I want you to think about this in this way. So I've drawn two different objects here. This first object is a block. It's a block that has 4 atoms in it. Obviously it's hypothetical, it's just a thought experiment, that's okay. Here's a second block that has 8 atoms in it. So my question for you is this. If you think about it and you apply a force, well, I'm going to draw in a force vector here so you can see it. Like that. That's a force being applied from the outside. So if we draw in that force right there, you can think about it like 1/4 of that force is being applied to each of those atoms. And so if you think about it, it's only 1/4 of the force that's actually being applied to each of the atoms to change its motion. And so it kind of gets divided up. You can see if we apply the same force, I'm going to draw it the same length and in the same direction to this larger block. Now all of a sudden that same force is being divided up over 8 atoms. And so you can think about the fact that that same force will have less of an effect on the overall change in motion of this second object because its force is divided up over more matter. And that's the whole property, that's the idea of inertia, that the more matter there is in an object, the more difficult it is to change its motion. So I would have to apply a much larger force to be able to get the same result on this larger block than I would this smaller block. And in fact, we'll find out that, and this is one of the things that Newton came up with, is that if you double the mass, to get the same change in motion, you must double the force. So they're directly proportional, which is a pretty big deal. But it makes sense from a logical standpoint, right? If I have 1/4 of this force is being applied to each of these atoms, now only 1/8 of that force is being applied to each of those atoms. I must double the size of this force to get the same 1/4 force on each of the atoms. Hopefully that makes sense. So the force is changing the motion, but the mass is resisting that change in motion because it's really dividing up the force that you have. What a change in motion is called is an acceleration. And so you might remember that in the last video we talked about how acceleration is the change in velocity in the change of the amount of time. And so it's what we call the time rate of change of velocity. It is a vector, and so I've drawn all of those 3 with vector arrows over them so you can remember that they're vectors. So it does have direction as well, so you have to keep that in mind. Now, an acceleration is always caused by an unbalanced force. That makes sense, right? Remember Newton's first law said if there are no unbalanced forces, the motion stays the same. And so if there is an unbalanced force, then there must be some change in motion, which we would talk about in terms of acceleration. We call that unbalanced force a net force. So just kind of remember that term because it's going to come back again and again and again. A net force is what causes an acceleration. So here we are. We have a net force causing a change in velocity, which we call acceleration. And we have this unbalanced force over here that's causing a change in motion to a mass. And so you can see we really have 3 variables we're dealing with: force and mass and acceleration. And so Newton's genius was to put those 3 together in a mathematical way. And he said if you choose the right units, and that's an important one we'll talk about in a second, if you choose the right units, you can figure out how much acceleration there is by looking at the amount of unbalanced force, or net force, and dividing that by the mass. Why dividing it by the mass? Because don't forget that the mass is a resistance to a change in motion. So the more mass there is, the actual less change in acceleration there should be. So as this number on the denominator gets bigger, this should actually go down. That makes sense, right? It's that, remember that mass is dividing up the force, and that's the key. Now, this is the way Newton said it. An acceleration is caused by a net force and resisted by a mass. We don't usually write it like that. We actually go ahead and write it in a way that's a little bit easier to remember, but not quite so easy to explain. So I'm going to go ahead and erase that and rewrite it as this. This is Newton's second law. The net force is equal to the mass times the acceleration. F equals ma. If you wanted to pick a starting point for physics, this is kind of it right here, Newton's second law. It's a big deal. So F equals ma. Now, remember a few minutes ago I said if you have to choose the right units for this to work. And so let's look at the units here. So the units for mass we learned last unit are kilograms. So I'm going to go ahead and write that in the square brackets here, kilograms. And the units for acceleration we learned in the last unit are meters per second, or meters per second squared if you want. And so whatever our units for force are, they're going to have to be kilograms times meters per second, which is kind of a yucky unit to have to write all the time because we deal with forces a lot. And so we are going to make that into a special unit named after Sir Isaac himself. And we're going to say that forces are measured in newtons. And so I'm going to go ahead and write a capital N here. I always put a capital N for newtons, and I always write newtons with a capital N. Your textbook writes it with a lowercase n. There's an old joke in physics that you know you've really made it in physics if they give you a unit and they start writing your name with a lowercase letter. So Newton can be written with a lowercase n. I highly recommend, though, when you abbreviate it, use a capital N. So that's how it goes. So forces are always measured in newtons in the metric system. In the imperial system, in the U.S., here we'd measured it actually in pound force. So I weigh about 175 pounds. That's a force. That's the force of gravity that's acting on me right now. So we could talk about pounds as a force, but that's in the imperial system. That's in the United States. In the metric system, we have to use newtons, and so this has to be in kilograms, and this has to be in meters per second. So just kind of keep that in mind. So that's it. Hopefully that makes sense. If you have any questions, please let me know. Thanks for watching.